Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video, we will continue chapter 10. We'll talk about the Betke-McMullen decomposition for H-star polynomials. Let me remind you about the previous video. We talked about the situation that we have an integral polytope with a unimodular triangulation. And in that case, the H-star polynomial, the numerator of the Erhard series of the polytope, is given by the H polynomial of the triangulation. We already said this is a very special situation. What we'll do now is prove a generalization, if you want, of this theorem 10.3 to the general case. We have an integral polytope and we have some triangulation, not necessarily unimodular. So here's the theorem that we're after. This is a famous result due to Betke and McMullen from the 1980s. I will talk about the ingredients in a moment. I want you to see the structure of this theorem. So we're given an integer polytope and the triangulation. And you can see that we can now write the H-star polynomial, so this numerator of the Erhard series, using some ingredients from the triangulation that we'll see in a moment. So this is not as clean as the situation with unimodular triangulations, but again, unimodular triangulations are very special. On the other hand, we know that any polytope has a triangulation, and so this theorem really has no condition other than the polytope being an integer polytope. Anyway, let me start to introduce the ingredients. These polynomials b sub delta, they're called box polynomials. And they're defined as follows. So delta is some simplex in our triangulation. It's a lattice simplex. It has integer vertices. And so we have the old, by now, construction that we cone over the simplex. And then, as we know, the fundamental sort of arithmetic data is in the fundamental power pipette that we usually call pi because I have many simplexes now, I want to write this as pi of delta. So every simplex delta comes with a fundamental parallel pipette. And then from here, we computed the integer point transform. And to compute the Erhard series, we eventually plugged in the values all 1 except for the last variable. And this is the H-star polynomial of delta. So this was described in chapter 3. What we'll do now is we will consider the relative interior of this fundamental parallel pipette. But other than that, it's the exact same construction, and this is the box polynomial of delta. It's a valid question to ask, why is this useful? One indication is, well, eventually we will get this theorem 10.4 here on this page, and you should think of this theorem giving structure to the H-star polynomial. So we can somehow write the H-star polynomial of a polytope as a sum over supposedly easier polynomials, or rather product of polynomials. One thing I invite you to think about at this point is that these box polynomials are palindromic. Namely, I claim if I think of them as polynomials sort of off degree dimension of the simplex plus 1, then these box polynomials have symmetric coefficients. They're all palindromes. That's number 1. And number 2, because they come from an integer point transform, you can realize that they all have non-negative coefficients. So the philosophy of this theorem is somehow we're writing the h star polynomial of P, we're decomposing it as a sum over polynomials that have sort of additional structure. So these box polynomials, they are palindromic and they have non-negative coefficients. And so what we'll do next now is to talk about this second ingredient here. These are h polynomials of certain parts of the triangulation. So let me remind you. So we started with some polytope P and a triangulation T. So this is a full triangulation, not just a boundary. Here's the h polynomial of this triangulation. The ingredients are the face numbers of the simplices appearing in the triangulation. Let me go back again to the theorem from the last video, when we have a unimaal triangulation, and review the reason why the h polynomial of the unimaal triangulation appears, because the starting point for the Betke-McMullen theorem will be exactly the same. So the way I think about my triangulation is I will take the relative interior of each simplex in my triangulation, each simplex in each dimension, and then write the polytope as a disjoint union over these relatively open simplices. A picture is worth 1,000 words. I hope this picture tells exactly what I mean. This disjoint union gives rise to a way of computing the Erhard series of my polytope. Here it is. I'm writing the Erhard series as the sum over the Erhard series of the relatively open simplices in my triangulation. And of course, for the open simplices, I will use Erhard-McDonald reciprocity. Here it is. For the Erhard series, I'm plugging in 1 over z. And so you can see the h star polynomials of each simplex appearing here. And now I will use a rewrite of the h polynomial. Here it is. So I claim my h polynomial can be written in this sort of rational function-looking form, where I'm summing over all simplices in my triangulation. And so this form of the h polynomial appears naturally when you simplify the expression that we have here for the Erhard series. And this gives rise to the theorem that we talked about in the previous video. Okay, this was a preview. Let me now introduce the ingredient that we need in the general case. We don't necessarily have a unimodular triangulation. So we need the notion of a link of the simplex in a triangulation. So here's the definition. You're fixing delta, is one of your simplices, in T. And the link are now all simplices omega in the triangulation with the following two conditions. They don't meet delta, a disjoint from delta, but they're contained in some common simplex in the triangulation with delta. One way to think about the link is look at all simplices in the triangulation that contain delta, and then the link will consist of all simplices in this bigger simplex that are disjoint from delta. On the right you can see an example. So I have a triangulation here of the cube, and I think of this vertex here as one of my zero-dimensional simplices in a triangulation. You can see a picture of the link of this vertex. As you might imagine, we need an h polynomial for this link. Here's the definition. In section 10.2 in the book, you can see a definition straight from phase numbers, but I like this definition here because you can see how it compares to the top line, my alternative definition of the H polynomial of the triangulation. So the sum over here is over all simplices containing delta. So again, I'm fixing simplex delta. I want to compute the H polynomial of its link. And so my sum over here is over all simplices that contain delta. And you might think about, what's the connection to the definition of the H polynomial of the whole triangulation? Well, this is the case where delta is the empty set. So for this, I need to declare a dimension, and I claim the correct dimension of the empty simplex in my triangulation is -1. And if you use that, you will see that the H polynomial of a link is a generalization of the H polynomial of the triangulation. At any rate, now we're doing exactly the same thing as in the case of a unimodular triangulation. So again, I'm writing the Erhard series of P as the sum of Erhard series of the relatively open simplices in my triangulation. Now the difference is that the H star polynomial of each simplex is not as simple anymore as in the unimodular case, but it turns out you can write this in terms of the box polynomials that we introduced in the beginning of this video. And once you do that and rewrite the expression that we have on the right here, the H polynomials of the links will appear just as natural as the H polynomial of a triangulation appeared in the unimodular case. So once you think of writing the H star polynomial of a simplex using box polynomials, the H polynomials of the links will appear completely organically. And this gives the Betke-McMullen theorem. Let me go back to my point of motivation for this theorem. We said this is useful because we're decomposing the H star polynomial of a polytope using sort of simpler ingredients. And so our next goal will be to now think of useful triangulations, because after all, we have a choice of what kind of triangulation we want to compute for this formula. And as we will see, if we're smart about this choice, we can milk this decomposition even more to say something about the H star polynomial of an integer polytope.